After getting to know about the gas laws, we can combine them to form what is called the ideal gas equation. The ideal gas equation, and it's really called the ideal gas equation since it is a really good approximation for those gases which approach the ideal behavior. So we will use three gas laws in this video. The first one will be the Boyle's law, and the Boyle's law relates the pressure of a gas to its volume. And it says that the pressure of the gas is inversely proportional to the volume. The larger volume you get, the lower pressure that gas develops. An equivalent representation of this will be to say that the volume is indirectly proportional to the pressure. The other law we will use is called the Charles law, and the Charles law says that with increased temperatures you are going to get increased volumes, and so V is directly proportional to T. Next law is called the Avogadro's law. Avogadro's law. It says something about the relation between the amount of gas you have, that is the number of moles of your gas, and the volume it occupies. So it says that the volume that a gas occupies is directly proportional to the number of moles it has, or the number of particles it has. What we can do from here is, if you look closely, in all of these three equations, in all of these three proportionalities, V is on the left hand side, so we can write a big V here. And we can combine all the other three right hand sides to form a giant combined gas equation. And this, if you combine that, there will be an N, there will be a T, and there will be 1 over P, so all of this divided by P. This forms from the fact that V is directly proportional to 1 over P, so you write that. V is directly proportional to T, so you write that, and V is directly proportional to N. From this, what we can do is we can replace this proportionality with equality, since we like equality more than we do proportionality. So to replace this proportional constant, you need to put in a constant. You need to multiply one of these sides with a constant. Let that constant be K. So we get that V is equal to the volume that the gas occupies is equal to N times T over the pressure times some constant K. And let's find what this constant is. Let's figure out what it is. Now, according to some data that I have, it says that there is a hot air balloon which has a volume of about 32,000 liters, to be exact 31,798 liters. This is the volume of that hot air balloon. The temperature at the time when this experiment was done is 21 degrees Celsius. The number of moles of this gas it's hydrogen, and the number of moles is 1300 moles. And the pressure, the atmospheric pressure, is 750 millimeters of mercury. What we can do is we can just put in these values. We can put in these values here. So we will take V, we will put it here. We will take T, we will put it here. We will take N, and we will put it here, and we will take P, and we will put it in the denominator. When we substitute all of that, you get two numbers here and here, and you can divide them to get the value of K. But before doing that, we need to do some conversions. And the conversions would be to convert this into standard units. So 21 degrees Celsius is not the best scientific way to write the temperature. The best would be to write this in kelvins. And this is equal to saying 21 plus 273.15 kelvins. For the sake of easiness, let's just forget that there is a decimal. So this will be approximately be equal to 294 kelvins. N is equal to 1,300 moles. that's standard. Let's just let the liters remain as well. Let's convert this mmHgs into atmospheres, since that gives us a better feel of the numbers in atmospheric pressures. Since one ATM has 760 mmHgs, 750 mmHgs is 750 mmHg over 760 mmHg per ATM. mmHgs cancel out. 750 over 760 is 0.9868, and this 1 over ATM comes up, and this is 0.9868 ATMs. Now what we can do is we can put in these numbers into this equation. So instead of volume, we will now write 31798 liters is equal to, number of moles is 1300 moles, times the temperature is equal to 294 kelvins, divided by the pressure. So the pressure in this case is 0.9868 ATMs. Let me shift this to the left a bit. And then what is left? This constant K. This constant K, let's write it in pink. Now what you can do is you can cross multiply. You can take this and you can divide by this on both sides, and you will arrive at an expression of K that will look something like this. It will look as K is equal to 31798 liters. That remains. This goes on the top, so it will become times 0.9868 ATMs. All of this divided by the number of moles, 1300 moles, and 294 kelvins. Solve for this, and I won't do this since it just takes a lot of memory of my brain, but once you do this, and it's written in textbooks as well, this will come, depending on the accuracy of your calculator or your brain, this will come out to be roughly equal to 0.0821 liters atmospheres divided by moles times Kelvin. And this right here is the value of the proportionality constant that you have. Now, K isn't the best constant that we use, and the reason for that is that K, small k, capital K is reserved for kelvins and small k is reserved for the Boltzmann constant. We'll come to that in a minute. So what we use here is instead a special constant, and it's called the universal gas constant, and it's denoted by the letter capital R. So instead of writing K, which was just sort of de facto proportionality constant, we will use R when we are talking about ideal gases and in other parts of science when you come to do this. So if you want to rephrase the ideal gas equation, the combined equation that you have, what you will do is you can take this pressure and you can multiply it on this side. And so in the end, you will arrive at P times V, that's equal to N and T remain, and that R, that universal gas constant, also comes here. And just to write it in a more favorable term, you can write this as P times V equals nRT. This is a really, really nice approximation to the ideal behavior of gases. Here, the value of R, what we have just derived from the example, is 0.0821 liters atmosphere divided by moles per Kelvin. There are some other representations of it. You might see this unit. You might see 8.314 joules per moles Kelvin. This is just the same. Instead of joules, since joule is just newtons times meter, you can write newtons times meter as Newton per meter squared times meter cubed. Newtons per meter squared is just pascals. So 1 joule is equal to 1 pascal meter cubed. Instead of writing joules here, you could have also written, and I will write that, you can also write 8.314 times pascals meter cubed divided by moles times Kelvin. You could have also derived this from this. It's just a plain conversion, nothing different. And this video sort of gives you the idea from where the ideal gas equation comes from. We will come and revisit this equation several times over the study of gases and science in general. See you in the next videos.